Class 10, Chapter 1 Real Numbers. Numbers which can be represented on a number line are called as real numbers and are represented by capital R. First concept in this chapter is fundamental theorem of arithmetic. The statement of fundamental theorem of arithmetic is every composite number can be expressed as or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. Let's see with an example. Over here, if you see the example, I have taken number 9, which is a composite number. We can write 9 as 3 times 3. So 3 times 3 is a prime number. So we know that 3 times 3 is 9. And another example would be 12. We can write 12 as 3 into 2 into 2, which is again a product of primes. We can express a composite number as a product of primes. This statement can be otherwise stated as the prime factorization of natural number is unique except for the order of its factors. Now, the next concept in this chapter is HCF and LCM. We know the full form of HCF and LCM. HCF is highest common factor and LCM is least common multiple. How we can find HCF of two numbers or two integers, say A and B. HCF of A and B is nothing but it is equal to product of the smallest power of each common prime factor in the numbers, and LCM of A and B, the same numbers or integers, would be product of the greatest power of each prime factor involved in the numbers. For example, over here I have taken HCF of 6 and 20, which is nothing but it is 2. 2 can be written as 2 raised to the power 1. And similarly, if we take LCM of 6 and 20, we get 2 square into 3 power 1 into 5 power 1. From this concept, we can arrive at an important result, which is nothing but for any two positive integers A and B, HCF of A and B and product of HCF of A and B times LCM of A and B is equal to A into B. I am repeating again, HCF of, that is highest common factor of A comma B into LCM of A comma B is nothing but A times B. Next, we know what are prime numbers, even though I have mentioned here. Numbers whose factors are themselves and 1. For example, if we take 2, 3, 5, we can write 2 as 2 times 1, 3 as 3 into 1, 5 as 1 into 5 or 5 into 1. No other factors are possible. Such numbers are called as prime numbers. Composite numbers. Numbers like 6, 8 who have factors other than themselves and 1, like 8 into 1, or we can write, so over here we can write 8 as 8 into 1 or 2 into 4. So here we can say that 8 has other factors other than 8 and 1 itself. Moving on to the next topic. So moving on, theorem 1.2, let P be a prime number. P be a prime number if P divides A square, then P divides A, where A is a positive integer. So proof is given by, let the prime factorization of A be as follows. A is equal to P1, P2 up to Pn, where P1, P2 up to Pn are prime numbers and not necessarily distinct. That is, it is not necessary that P1, P2, Pn are different prime numbers. Therefore, A square equals P1, P2 up to Pn into A square. We know A is P1, P2 up to An. So, if we take square of it, P1, P2 up to Pn into P1, P2, P3 up to Pn, we get P1 square into P2 square up to Pn square. So, it is given that P divides A square. Therefore, by the fundamental theorem of arithmetic, the only prime factors of A square are P1, P2 up to Pn. So, P is one of the, so we can say that P is one among P1, P2 up to Pn. Now, since A is equal to P1, P2 up to Pn, we can say that P divides A. Hence, we have proved the statement. So, hence proved. Now, next is theorem 1.3. We have to prove that statement is root 2 is irrational. Moving on to the proof, we are taking the assumption as, let us assume to the contrary that root 2 is rational. So, we are using the contradiction method that root 2 is rational. First, we are assuming that root 2 is rational and we are going to prove that it is irrational. So, we can find integers p and q. So, we are taking two integers p and q where q is not equal to 0. We know that this is the format and definition of rational number such that root 2 is of the form p by q. Suppose p and q have a common factor other than 1. Then we divide by the common factor to get root 2, which is equal to p by q, where p and q are co-primes. So, when we divide root 2 by the common factor, so then we get q root 2 equals p. Now, squaring on both the sides, we get, now when we square on the both sides, LHS as well as RHS, we get q root to the whole square is equals to p square. We get 2q square equals p square. So, therefore, 2 divides p square. By the statement of theorem 1.2, we know that let p be if p is a prime number and p divides a square, then p should also divide a, and a is a positive integer. From that theorem, we can say that 2 divides p. So, we can write p equals 2 times r for some integer r. Now, substituting for p, we get 2q square equal to 4r square. So, when we calculate for q square, it is equal to 2r square. This means that 2 divides q square, and so by the previous theorem, that is theorem 1.2 statement, we can say that q square equal to, when we substitute for p, we get 2q square equal to 4r square. For simplifying that, q square equal to 2r square. This means that 2 divides q square. From this, we can say that, from the previous theorem, we can say that 2 divides q. Therefore, p and q have at least 2 as the common factor, but we have taken the contradiction that p and q are co-primes, but so from this statement, it contradicts that p and q have no common factors other than 1. This contradiction has arisen because of our incorrect assumption. So, we have proved that our assumption that root 2 is rational is wrong. So, we can conclude that root 2 is irrational. Hence, We have proved that root 2 is irrational. Now the next concept is, we know that HCF of A comma B or P comma Q into LCM of P comma Q is nothing but product of P times Q. But when we take HCF of three numbers or three integers like P, Q and R and LCM of P, Q and R, it is not equals to P times Q times R, where P, Q, R are positive integers. But it satisfies the condition LCM of PQR is nothing but PQR, that is P times Q times R in. I am repeating again, LCM of PQR is nothing but it is equal to PQR, that is P into Q into R times HCF of PQR divided by HCF of P and Q into HCF of Q and R into HCF of P and R. Similarly, HCF of PQR can be calculated as P times Q times R into LCM of PQ and R divided by LCM of PQ into LCM of QR into LCM of PR. That's all for today's video. In this chapter, now next we will be seeing the next chapter in the next video. Thank you guys.